Mobile Graphical User Interface, GUI. Agents have revolutionized smartphone automation by leveraging multimodal large language models and system-level control interfaces. These agents can navigate apps, fill forms, retrieve information, and execute complex multi-step workflows, essentially acting as digital assistants that take over your phone's interface. But this power comes with a serious cost: privacy. Because these agents rely on full-screen captures, either screenshots or structured XML hierarchies, they inevitably expose sensitive personal data. Phone numbers, addresses, messages, verification codes, financial details, everything visible on screen gets sent to the cloud. In some systems, this data isn't just transmitted. It's cached, stored, and reused, creating long-term privacy risks. Even when agents are designed to minimize exposure, they often fail to protect task-critical sensitive information. Existing defenses fall into 4 categories: reducing UI exposure, obfuscating content, relying on user authorization, or replacing PII with generic labels. But each has a fatal flaw. Either they leave sensitive data exposed, degrade usability, or break the agent's ability to act. We propose a fundamentally different approach, making sensitive data available but invisible. Our framework ensures that agents can use private information, like entering a phone number or validating a payment, without ever seeing the real value. This is achieved through a layered, privacy-preserving architecture built around deterministic, type-preserving anonymization. Here's how it works. When a user issues an instruction, say, add a contact named John with a phone number 12,345,678, our system first detects sensitive elements using a hybrid PII detection model. We combine a label-guided zero-shot NER model from the Geely NER family with regex pattern matching. The NER model identifies entities like phone numbers, emails, or names based on semantic context, while regex handles high-entropy identifiers like credit card numbers or ID codes. Crucially, we apply instruction-driven contextual whitelisting. If a string appears in the user's instruction and is classified as non-sensitive, we treat it as safe throughout the session, preventing over-anonymization. Once detected, each piece of sensitive data is replaced with a deterministic placeholder. For example, the phone number 12,345,678 becomes phone number #3GA8F. The placeholder is generated via a cryptographic hash, SHA-256, value plus type, encoded in base 36 and truncated to 5 characters. This ensures the same input always produces the same output, no randomness, no collisions, and preserves the semantic category so the agent knows it's still a phone number. This anonymization happens across all modalities. In the XML hierarchy, text attributes like text, hint, or content desk are replaced. In screenshots, OCR extracts text, which is then fuzzy matched against known entities using Levenshtein distance. If a match is found with a confidence above 85%, the corresponding placeholder is reused. This cross-modality consistency is critical. If the agent sees first name #0T3IA in the instruction but first name #G7WEF on the screen, it can't ground its actions. Our system avoids this by maintaining a session-scoped local mapping table, a secure, in-device record of real values and their anonymized equivalents. This table never leaves the device, ensuring raw data remains private. The anonymized interface, the virtual UI, is then sent to the cloud-based agent. The agent operates entirely on this sanitized view. It can reason about the layout, interpret interactions, and issue commands using placeholders. But when it tries to act, the secure Interaction Proxy steps in. This layer intercepts every command and resolves it back to the real world. Take a type str command. If the agent says, type first name #0T3IA, the proxy identifies the placeholder, looks up the real value John in the local mapping table, and sends the actual string to the phone via ADB. Spatial actions like tap num or swipe num dire are handled differently. The agent refers to elements by numeric index, which maps to a bounding box in the XML. The proxy validates the index, converts it to device coordinates, and executes the gesture, all without ever exposing the real content. Now, what if the task requires reasoning over raw values? For example, comparing 2 dates, checking if a payment amount is valid, or validating a password format. In these cases, the agent can't operate on placeholders alone. Our solution, a privacy gatekeeper, a small local language model SLM that performs tightly scoped computations. When the agent requests a calculation, it sends a structured query. Cloud agent compute with tokens, instruction, reason. The gatekeeper checks 3 policies: relevance to the task, necessity of raw values, and whether the result can be expressed minimally, like a Boolean or categorical label. Only if all passed does it compute locally and return a safe result. True, valid, greater than, never the raw data. This layered design ensures strong privacy without sacrificing utility. We tested our framework on 2 benchmarks: AndroidLab, which evaluates general-purpose mobile automation, and PrivScreen, a privacy-focused dataset with synthetic PII injected into real app screenshots. On AndroidLab, our method caused only a modest drop in task success rate, around 3-4 percentage points under SOM mode, but preserved rational behavior and screen change effectiveness. In XML mode, performance even improved slightly, suggesting that anonymization helps filter noise and focus the agent on task-relevant structures. On PrivScreen, the results were striking. Our method maintained near-perfect utility, 90% accuracy on GPT-5 and QN2, 5VL7B, while slashing privacy leakage. The leakage rate dropped from 97% to just 19.5%, and BERT's score, a measure of semantic similarity between original and leaked content, plummeted from 0.926 to 0.149. Compared to strong baselines like dual-tap, our approach achieved the lowest leakage across all models, while maintaining competitive accuracy. Performance overhead is also reasonable. The full pipeline, OCR-NER anonymization, adds about 1.77 seconds per image on average. This is acceptable in mobile automation, where tasks span dozens of steps and latency is not critical. Crucially, our framework doesn't just protect data, it redefines how we think about privacy in agent systems. We distinguish between data usage and data understanding. For usage, like filling a form, the exact value doesn't matter as long as the placeholder is consistent. For understanding, like comparing dates, the agent needs semantic access, not raw content. Our system supports both by combining anonymization with local semantic augmentation. This work reveals a deeper truth. Current GUI agent architectures are structurally flawed. They depend on raw visual input because mobile OSes lack native, LLM-friendly interaction protocols. This forces agents to see everything, leading to systemic overcollection. Our solution works within today's constraints, but it points to a future where mobile interfaces are semantically structured, privacy-aware, and designed from the ground up for secure agentic workflows. In conclusion, we've presented a novel, practical privacy protection framework that enables mobile GUI agents to use sensitive data without seeing it. By enforcing available but invisible access through deterministic anonymization, cross-modality consistency, and secure local computation, we achieve the best privacy, utility trade-off to date. This isn't just a technical fix, it's a step toward trustworthy, real-world deployment of AI agents on personal devices.